I started this KiCad project a little different than normal. The new power supply has got to mount in the same location as this old power supply. So the mounting holes and the power jack need to be in this same exact location relative to these two edges of the PC board. The board can grow a bit wider to the inside, and of course it can be almost 2 inches longer if it needs to be. I don't see I'll need that much space though. I thought about measuring the location of the parts and then placing them, hopefully in the correct position, but that seemed like a problem in the making. So instead of starting a new project, I used the save as command and saved this version 1 power supply to a new name, and I'm going to use that as the version 2 power supply project. For the schematic, moving a few of the parts, adding some parts, and replacing a few of the parts. Of course, the flyback section of the schematic looks quite similar to version 1. So that really worked quite well for the schematic layout. And with the schematic done, hope I didn't miss anything, it's time to move to the board layout. These two edges have to stay in place, kind of the reference points to work with. The power jack will stay and the two mounting holes, and I won't move them at all, at least relative to each other. I can make the new board up to a 1/2 inch wider, and I'm adding quite a bit of circuitry to the version 2 power supply, but I don't think I will need more than an additional 2 square inches. So I'm going to increase the width of the board by 0.2 inches. That way the length of the board shouldn't have to be extended more than an inch. I don't really want to add another support for the PC board. I'll delete some of the traces and fills at the input section. I'll get rid of some of the footprints too. It really works great. If I import a part with the same reference number as one that is still on the board, it doesn't cause a problem. Both footprints can coexist on the board. If I click on the part in the schematic, it will highlight both parts on the PC board. Then I can delete the one I don't want. That way I can leave some of the parts in place so I can see how I laid them out for the first version. I think that will save me a bit of time routing traces. Several hours later, I think I have it. Only ended up being a 1/2 inch longer than version 1, so I'm very happy with that. Normally, before ordering the board, I would let it set overnight and take a last look at it with fresh eyes. I'm going to risk it with a few looks over with tired eyes. Hopefully I won't regret it. I always like seeing my new PC boards. They look so shiny and full of possibilities. I'll sand off what's left of the panel tabs and get to mounting some parts. I'm going to mount a few of the power input parts first. I got the board a little on the hot side for the solder paste. I'm still loving the solder paste and hot air. I think I've kind of blocked out the memories of mounting a bunch of SMD parts before the hot air station. For the power jack, I'll add a bit more solder with the iron. A lot of mechanical stress on that part. Before I move to the next section, I'll put power to this, make sure I don't have any shorts. The next section is going to be the 12-volt buck regulator for the fan power. This is the first time I'm using this type of capacitor. Kinda looks like better to hand solder them instead of the hot air. I did away with all through-hole filter caps for this. These polymer caps have much better ESR values at high frequency. My voltage feedback resistors are not quite the values I need, so my output voltage will be a bit on the low side, probably around 11.8 volts. I had to replace the Q1 transistor. Something wrong with the leads on the first one. Solder would just not flow on the leads. I plan on replacing this 3904 with a MOSFET anyway, next time I order parts. I'll test this section, make sure it works before moving on. I'm feeding into a 60 ohm resistive load here, so close to 200 milliamps. The enable line on the connector has to be pulled low to enable the fan power, so if the fan connector is unplugged, the buck regulator will be disabled. Here's the noise output on the 11.8 volts with the resistive load. Bit over 50 millivolts. Real test will be what it looks like when the fans are running, but good so far. Now most of the flyback controller parts get installed. With this layout, I made room for a bit more input filtering for the controller. I really wonder if that instability I had with the first power supply was caused by weak input filtering. Again, I'm overdoing it with the solder paste. I've left out this resistor here for now. That way the controller is enabled once the voltage is above the chip's minimum value. and the overvoltage protect is disabled. I want to bring the voltage up slowly, make sure my waveforms look okay. Very important this voltage clamp here is working properly. Don't want to fry the controller before even getting started. The 4 rectifiers and 4 10 microfarad capacitors get installed. I really hate that this coil former didn't have gull-wing terminals. These J-form terminals are going to be hard to solder. My magnet wire coating is about the lowest temperature, so I don't really trust using the hot air gun on it. So I'll put the bent tip on the soldering iron and see how that does. I do think these terminals will make for a very strong connection to the PC board. They should hold a lot of solder. Of course, the downside is, it will also make it tough to remove. Say for some reason if I have to change the windings. Okay, first test of the flyback controller. I've got a 500 ohm load on what should be about 14 volts, and I've got 50 ohms on what should be 5.1 volts. One thing I did do for this layout was to put 2 resistors in series for the voltage feedback circuit, just to make it easier to fine-tune the output voltage. But I really think 5.07 volts is going to be fine. The switch node waveform looks like this. As I power up the circuit, what I look for first is the peak voltage of this turn-off spike. It absolutely has to stay below 80 volts. I'm at 20 volts input here, so a peak spike just under 60 is right at what I would expect. A 36 volt Zener plus a diode drop plus the 20 volt DC input voltage. Of course, the Zener voltage can vary quite a bit. Now at this point, I don't have any snubber in place. Can see there is quite a bit of ringing here. It dies out well before interfering in the voltage regulation, but it's probably a pretty high frequency that I don't want being radiated. So ringing is at about 25 megahertz, probably would be a bit higher if I didn't have the scope probe on it. And with a 100 picofarad capacitor across the primary winding, the ringing drops to 17.5 megahertz. I'll feed these values into TI's 7-step snubber design formulas. And with the closest values I have of 330 picofarad and 51 ohms, I end up with this. Maybe a bit overdampened, but plenty close enough. I'll put the rest of the filtering parts and regulators on, and let's see what we get. At this point, the only parts not installed are the input ground to isolated ground capacitor and resistors, and the snubber parts for the rectifiers. Well, still a few test point sockets to install, but getting near the end. And still have to install the resistor to enable the undervoltage lockout and the overvoltage input protect. Okay, a few more items to go till it's ready to install in the load. First, this is the undervoltage lockout. Let's see what values I ended up with. The meter on the right is the input voltage. The one on the left is the 12 volt output. Looks like about 14.7 volts to get it to start. That's just what I want. It shouldn't run with the 12 volt power supply plugged into it. I might want to raise that just a bit. Looks like it drops out at 13.2 volts. This value is not really that important. Now for the overvoltage test. Seems to kick in around 28.8 volts. I might end up raising that a bit. As long as it shuts off before 32 volts, should keep the flyback controller safe. Here's with my 24 volt power brick I plan on using with it. I'm at 25.1 volts, so about 3.7 volts below the cutoff. Probably will be fine. If I end up with a 4 volt spike on the output of the power brick, probably something's gone wrong with it. Okay, now for the big test. Did everything stay aligned during the PC board layout? It looks like it. Not a bad fit. Bit larger, but it doesn't bump into anything, so I think I'm good. Well, fans are running, lights are lighting. From a superficial point of view, everything looks great. I'll do one final check of the voltages. Input voltage good. Fan voltage 11.86 volts. I've got to order some resistors to get that to where I want it. Now the outputs to the control board. The 12 volt supply is 11.86. It's not connected to the fan voltage, just one of those crazy things. 4.2 volt output is 4.2 volts. 6.01 volts out of the 6 volt rail, and a minus 6 volts for the negative 6 volt rail. All in all, looks good. The 12 volts a little lower than I would like, but it's off by just a bit over 1%. Really can't ask for much more than that from a cheap little regulator. But the question is, did the new power supply fix the problems I was having? This is now the waveform on the 12-volt rail at the control board, where it is sent to the power MOSFET modules. What ripple is now there is not at the power supply switching frequency of 123 kHz. It's at the display I/O board's buck regulator frequency of around 700 kHz. I do want to see if I can stick an input inductor on the display I/O board, but I don't see this getting through the filters on the power MOSFET modules. So here's the waveform at the load terminals. The load is connected to an unregulated 600 watt linear power supply, and I'm running at a 1 amp load. At first I thought, noise spikes from the power supply switching, still? This is the switching power supply waveform, and they don't line up. Then I realized I still had the LED ring light plugged in, so I unplugged it. Now this is what the load terminals look like at a 1 amp load. That I can live with. And it also reminds me I need to find a better power brick to run the LED ring light off of. At 10 amps, still looks very good. Certainly the 123 kHz power supply ripple is now gone from the output of the load. I would say mission accomplished. I'm happy with it. I'm sure if I would have spent a bit more time I could have packed things in a bit better, but it ended up being smaller than I was expecting. I'm very glad I went with the RM cores over the pot cores, and being able to get the core formers makes life so much easier. Separating the fan power from the other loads, I should have done that in the beginning. Here is the power to the fans with both fans running. Little buck regulator I would say is doing a very good job, considering how uneven the current draw is going to the fans. Very happy with that. Hardware-wise, what's left? The new power MOSFET modules, but I'm going to live with the modified ones for the time being. We'll have to make a fan control board. Of course, it will have to have a couple of photocouplers on it, now that the fan power is not isolated from the incoming power. Hardware seems to be very close to being finished. Software, well, that's just getting started. And to be honest, I think the software part may turn out to be harder than the hardware part. May have to take a step back every now and then, but forward the project marches. Thank you for watching.